Hello everyone. In this occasion, I would like to present our work, titled, Automated Identification of Libraries from Vulnerability Data. Can we do better? First, let's talk about the motivation of this work. In recent times, we observe increasing usage of third-party libraries. Library users need to be aware of the library vulnerabilities that may affect their applications which utilize vulnerable libraries. National Vulnerability Database curate vulnerability reports which contain the details of vulnerabilities occurring in third-party libraries. These reports are often incomplete, as they do not include the list of all libraries affected with the vulnerability. Thus, human efforts are required to identify all the libraries related to the vulnerability. However, this requires significant time and resources due to the huge number of libraries available. Based on the described problem, we believe that an automatic approach to predict the libraries affected by a vulnerability report is required. Having this automatic approach will significantly reduce the human effort required to identify vulnerable libraries. Now, let's formally describe the problem. First, we have the vulnerability report as our input. This vulnerability report contains a unique ID, description of the vulnerability, a list of web references, and a list of CPE configuration. Then, we utilize machine learning models for automated related library predictions from vulnerability reports. Based on the given input, we expect the machine learning models to output the list of libraries affected by the vulnerability described in the input report. Previously, Chen et al. Has investigated this topic by utilizing FastXML, a traditional XML model. However, their investigation is still limited due to several reasons. First, they only evaluate one XML technique and did not investigate the usage of deep learning. Second, there are still room for improvements as their approach only achieved average F1 score of 0.64. Finally, more advanced XML techniques have been proposed recently. In our study, we investigate whether recent XML techniques can achieve better performance for the vulnerability report library identification problem. We investigate two research questions. First, do deep learning-based models and other recent XML models outperform FastXML in identifying libraries affected by a vulnerability? Second, how efficient are the different XML techniques? Our dataset comprises of 7,666 vulnerability reports containing 4,682 possible labels. We split this dataset into 6,017 training data and 1,649 test data. Note that the distribution of this dataset is skewed, with most of the vulnerability reports having one or two affected libraries. We conduct our experiments on 6 recent XML approaches, including DSMEC, Extreme Text, Parabel, Bonsai, XML-CNN, and LightXML. These XML approaches have been shown in their respective paper to have better performance compared to FastXML. To evaluate the performance of the models, we consider the top 1, 2 and 3 predictions and calculate 3 metrics, which are precision, recall, and F1 score. To compare the results between the models, we make use of the F1 score as it is calculated from the harmonic mean of precision and recall. Meanwhile, to measure the efficiency of the models, we measure their training and prediction time. We run each model 10 times and report their average execution time. For the performance evaluation results, we find that LightXML achieved the best performance with 10% average F1 improvement from FastXML. Meanwhile, Bonsai and Parabel also achieve good performance with 7% average F1 improvement from FastXML. For the efficiency evaluation results, LightXML requires longer training and prediction time compared to FastXML. Meanwhile, Bonsai and Parabel models are significantly faster with up to 627 times faster training and 13 times faster prediction. Through our analysis and experiments, we learned several lessons. First, we found that while transformer-based model, LightXML, has the best performance, it came with efficiency cost. Second, the tree-based models are a good alternative as they achieve good performance improvements over the baseline while also providing significant speedup. Third, our deeper analysis found that recent XML models can correctly predict rarely occurring labels in the dataset. Fourth, we also find that there are room for improvements. such as the need for more data sources and the need to predict libraries not seen in the training dataset. Thank you.